All right, welcome to the last class of algorithms and data structures. Today, we're going to cover a couple of things. So we're going to cover the greedy method introduction. So because MST or minimum spanning tree and Dijkstra are a greedy method algorithm, or they are greedy method algorithms. So first of all, we need to understand what a greedy method is. So a greedy method is similar to divide and conquer. Method. Which is an approach or a strategy some people call it an approach, some people call it a strategy to solving a problem. So you have a problem, like you would like to have you would like to find an algorithmic approach to it, like you would like to solve it, and that problem is can be solved either, for example, either in divide and conquer. So you can divide your problem into smaller manageable pieces, and then you tackle every piece alone. Like, for example, the merge sort, for instance, it's a divide and conquer algorithm. Or you can actually use the greedy method. Now, a greedy method is basically an optimization problem. Greedy method sorry, is not an optimization problem, used to solve an optimization problem. So greedy methods used to solve optimization problems. Okay. So what is an optimization problem? An optimization problem should provide a solution. So if you are optimizing a problem, should provide a solution with a minimum or maximum result. Or maximum result. Okay. So let's actually start to put this into practice. Like let's actually have something a little bit more concrete. So suppose we have a problem. So let's call this an example here. So suppose we have problem P. Okay. And the description of that problem, we want to travel from point A to point B. So practically speaking, you have a problem where you would like to go from point A to point B. Now the question boils down to is how many solutions do we have for this problem? I would like to go from city A to city B, from Mostar to Sarajevo, or from Sarajevo to Zenica or Tuzla, or whatever city you would like to go, or from, I don't know, from Sarajevo to Minhen, wherever, okay? They would like to go from point A to point B. What are the available solutions? One solution would be going by foot. Another solution would be, for example, going by bike. Another solution might be, for example, by car. Another solution could be by train. And another solution could be by plane. I mean, the list can go on, right? You can go on and on with that concept, right? Now we can introduce a constraint to this, and we can say, okay, you know, with that many solutions, I would like actually to grab, like to have, I would like to go from point A to point B in let's say in 2 hours. So for example, I would like to go from Sarajevo to Istanbul, for instance, and I would like to reach there, let's say in 2 hours. When you say that, when you put this constraint, this is called actually a constraint. Right now, your solutions will be actually limited, right? You will not consider by foot, you will not consider by bike, you will not consider by car, right? Because because none of them will satisfy this constraint, right? So a constraint can be introduced for this problem. For example, reach uh, reach to destination in 2 hours. Okay. Now, once this constraint has been introduced, it will reduce our solutions to two of them, S4 and S5, right? So S4 and S5. These are the possible solutions to satisfy that constraint, okay? Now, here is a terminology. A solution, or if, let it be like this, if solutions satisfy constraints, okay, they are called feasible solutions. Okay. Now, let's say we would like actually, so we have a couple of solutions, right? Right now. Now, I mean, we had 5, okay, suggested. With the constraint, a solution has been satisfied with the constraint. A bunch of 2 solutions have satisfied the constraint, so they are actually called a feasible solution. So we have two feasible solutions. So S4 and S5 are feasible solutions. So what happens if I would like to say, okay, this is all fun and games. I have two feasible solutions, but I would love to go by cheapest. Okay? I would love to go cheapest. Now this, when you say I would like to go cheapest, this became a minimization problem, right? So you are optimizing by minimizing, okay? So if you introduce additional constraint, so if introduced with the introduction of additional constraint, uh, for example, I want the cheapest solution, okay? Then this problem is a minimizing problem. Okay? I'm just giving terminologies here. You can have a maximization problem. For example, you could say, okay, I would like to have the shortest period, right? However, I would like to have the most max. So for example, I would like to travel there to get there in 1.5 hours or 1 hour. But however, I would like to have the most luxurious trip. I would like to go there by the most expensive train or the most expensive uh, way of transportation that gives me luxurious way of traveling. Similar to the Concorde airplanes, for example, like you are traveling by the supersonic speeds, for instance, right? So that's one way of putting it. Right now, it becomes a maximization problem. You are a rich guy, you would like to have fun, and you would like to travel comfortably with an interesting traveling methods. Okay. Now, it's important to mention here for any given problem, for any given problem. Oh, by the way, before I actually say that, I forgot to define this. So when we said, apologies, hang on a second. So when we said the maximize, this is actually a maximization or minimization problem. When I said the introduction of the additional constraint, like I would like to have the cheapest, the cheapest way of transportation or the most expensive way of transportation, I have said here that so this with the cheapest, for example, making it a minimization problem right now, the only solution which we have is S4, right? It became S4 because a train is cheaper than airplane. Okay, so a solution that satisfies this constraint, like satisfies all the constraints. Okay, so a solution that satisfies all constraints is called optimal solution. For any given problem. there is only one optimal solution. Okay? So this is very, very important. Which has to give me a minimum. So it has to provide a minimum. Oh boy. Or maximum result. The cheapest, the most expensive, the smallest, the shortest, the largest, whatever. So this is basically it. So basically speaking, greedy method. Oh man. Are used for solving optimization problems. Okay. Now, there are several other strategies, and I would like to mention them here just to be just for the sake of completeness. So strategies for solving optimization problems. You have the greedy method, which we discussed. You have something which is called dynamic programming. You have something which is called branch and bound. Okay. So you have like these three different strategies for solving optimization problems. We are discussing greedy method algorithms this class. I advise or I implore you to that you actually read more about dynamic programming and branch and bounds way of solving problems. So I think this is good for you to know about. Now, this is actually now with this introduction to greedy method is done, and now you have an understanding of what a greedy method is. You will see through the next two algorithms, which is the minimum spanning tree and Dijkstra, how we are actually solving, how we are in fact solving these problems. Now, a greedy method. It's important to understand that greedy methods um, they take one input at a time and solve the current problem given that certain input. So if you give it like something big, it will take one thing at a time and solve it. It doesn't look to the whole problem, but it just looks one thing at a time. So this is an important thing that you know about. All right, so let's talk about minimum spanning trees. Or for short, MSTs. Now, minimum spanning trees, or MST rather, is a graph that is a subgraph, which is actually, or let it be like this, is a graph. Which is a subgraph of an existing or given graph. Okay? It must include all vertices and the subset of edges. Okay? So this is super important. Now, it has to include all vertices and just subset of edges. Now, if I given the following graph, so if I give you a graph that looks like this, come on. So 1, come on, really, 2, 3, 4, 5, and 6. Now, please understand that a tree is a special kind of graph, if you remember from our previous class on graph theory. Okay, a tree is a special kind of graph. And minimum spanning tree has to be like so. And if you give a graph, I need a subset. I need a tree out of that graph, which makes a subset of the graph, because it includes all the vertices, but parts of the edges, not all the edges. Okay. So what could be the minimum spanning tree for this? I will actually pick up another color here, and I can say, okay, you could say that this edge, this edge, this edge, this edge, and this edge will form my minimum spanning tree. It included all vertices. It doesn't have any loops in it. And it just, like a subset of edges. So the question boils down here to what is the definition then? Okay. So for a given graph, so we know what a minimum spanning tree is when we look at it, right? So how can we satisfy the condition of a minimum spanning tree? For a given graph, we will call it G, okay? With set of edges E and set, oh, come on, set of vertices, which is going to be V. Okay, so practically speaking, we are saying like what I said in English, it translates to this V and E. Oh, really? There we go. Okay, a spanning tree S is a subset of graph G, okay, where V dash, which belongs to the like a set of vertices, which belongs to the tree S, is equal to V. Okay, so let me write it here so for you as a reminder. So V dash is the, oh, come on, or R the, is the set of vertices belonging to S, the tree S, and E is equal to V minus 1. Okay? This is by definition. So you included all vertices. So a minimum spanning tree, if you are, for example, in an exam and you're solving a minimum spanning tree, what you would do is say, aha, okay, I will actually include all vertices, so I have to include them all. So if your tree includes all the vertices, you check one condition. And the second thing here is that your edges has to be V minus 1. So for example, here we have 6 vertices. So we have how many edges we have here? 1, 2, 3, 4, 5, right? So we have 5 edges and a total of 6 vertices. And the minimum spanning tree, by definition, it says you have to include all the vertices, which are 6. It's already available in the set. And V minus 1 edges. So since we have 6 vertices, we have 5 edges. We satisfied the condition. This is actually a minimum spanning tree. And obviously, there are no loops. Okay, so the question boils down to here is like, what happens if I actually give you something like this? So what happens if I have one, come on. Stop glitching already. So 1, 2, 3, 4, 5, and 6. And let's say that you have something, oh, for real. You have something like this. Okay. And then you are asking about, okay, what is going to be the minimum spanning tree for this guy? So the minimum spanning tree for this guy would be something along these lines. I mean, there are many ways of making it. I mean, there are no directions. So this graph is not directed. And this graph as well is not, doesn't have any weights. So many things you can happen here. So I'm just gonna simply say for fun, I'm gonna pick up, for example, this. I'm gonna pick up this, right? I'm gonna pick up this one as well. I'm gonna pick up this one. I'm gonna pick up this one. This is a minimum spanning tree. There are no loops. I have all the vertices minus 1 edges. So we have 6 vertices. How many edges do we have here? 1, 2, 3, 4, 5. So I satisfied the condition. So this is a minimum spanning tree for this example. So what are the possible spanning trees for a graph, right? What is the minimum spanning tree? And right now, this is the optimization problem, which I was talking about. So what are, let's actually have this. What are the possible spanning trees for this given, for the following graph? And let's say I have a graph. I'm going to give you a graph that looks like this. So 1, 2, 3, and 4. And I'm gonna connect them that way, and you have here 6, 4, 3, 5, 7. Okay? And let's say, what's gonna be the minimum spanning tree? Well, you can actually have something like this. So you can say 1, 2, maybe here's gonna be 4, 3, right? With 6, 4, and 7. right? These are the actual edges here. And obviously I include all the vertices, and I have number of edges equal to vertices minus 1 of the original graph, right? So of the original graph, number of vertices minus 1, which is going to be three, which is meaning that I have a minimum spanning tree. What is going to be the cost? So the cost for this minimum spanning tree is the summation of all the weights. So 7 plus 4 plus 6 is going to be 17, right? Let's have one more. So you can say, for example, 1, 3, here 4, and there is your 2, right? And you have here 5, 4, 7. However, the cost for this guy is going to equal to 16. So 5 plus 7 plus 4. You have another one, and we'll stop right here so we don't 3, 4. For example, I could have 2 like this. So 5, 3, and 4. And we're going to have a cost of 5 plus 3 plus 4 is going to be 12. Okay. So this is practically speaking your cost. Now, as you can see here, we have several spanning trees and having several costs per valid spanning tree. However, we would like to find the minimum spanning tree, like with the minimum cost. Now, this will require us to apply some greedy algorithms, right? You could actually try this bit, but like you can actually like find all the spanning trees, calculate the cost, then get get the smallest cost, and then you get the minimum spanning tree, right? And this is like one solution to a problem. However, this is what we call a brute force solution, right? You try everything and then you pick up one, right? Which is not that very smart. Another way of solving this problem is using Prim's and Kruskal, which are super Prim's or rather Kruskal's algorithms to find the actual minimum spanning trees. Okay. So it is 1 o'clock. I will actually give you a short break. So I'm gonna so it's 1 and 1. So let it be until 1 and 10. So I'll give you a short break, and then after the break, we'll get back and we'll solve the Prims and the Kruskal's algorithms and see also Dijkstra afterwards. Okay. So see you after the break. And if you have any questions, please feel free to post them here in the chat. Thanks. All right, and we are back. Since there are no questions from anybody to answer, so we can move along. Prim's algorithm, super simple, easy. We can actually start with it. Prim's algorithm, Prim's MST algorithm. Now, Prim's minimum spanning tree is super simple. If I give you a graph that looks like this, so let's say 1, 2, 3, try to make it as nice as possible, fighting all the glitches. 4, 5, be like this. Here 6, connect 7, and then I'll connect this guy here, connect this guy here, connect this guy here. Okay, and let's say we have here a weight of 10, 28, 16, 12, 14, 24, 18, 22. We'll say this one is going to be 25. Okay, so we have a graph with weighted edges, and we would need to find a minimum spanning tree. So what Prim says, first of all, get the edge with the smallest or the minimum cost. Okay, edge with the minimum cost, like the smallest cost possible. So the smallest cost possible here is actually 1 to 6, right? So 1 6 is the smallest edge. So I'm actually going to put the solution right here. Let it be like this. So let me grab this guy, and I'll just move it just aside a bit right here. Okay, and then I will grab the pen, and I will actually write this down, maybe in a different color. Let's say this one. So here is going to be, come on, 1. Maybe yellow would be better to be more visible. 1 and 6 with a cost of 10. The next step, I know how to write, get the next smallest and connected edge. And this is very important, the connected bit. So, and you repeat the process. So these are just simply like this, these are the 2 steps. So practically speaking, you say, okay, I see. So 1 and 6. So what is the directly connected ones? You have 1, 2. So you have this edge. So this edge, and you have that edge, and you have to choose the smallest. So I'm going to choose the smallest, which is 25. So practically speaking, I'm going to go right there. So this is going to be 5. And this is 25. Oh, come on. 25. Okay. Now you're going to actually pick up the next connected, but smallest, right? So here's going to be, we have 24, 22, and 28, right? Reaching out from here. So reaching out from 6, you have like, so we have this 5, right? So this 5 is connected to this one, which is already has been considered, so we don't look at it. Connected to 7, connected to 4, and still from the 1, right? From 1, which is here, we are still connected. We are still connected to 2. So which one to pick? I'm gonna pick up the, whoops, let me undo that. So I'm gonna pick up the smallest, which is 5, 4, which is gonna be 22. Then we need to look at the smallest. Now, what is the smallest connected? So the smallest connected, you have 28, 24, you have 18, you have 12. Right? Right now, these are the ones which we have to consider. So because 12 is the smallest, I'm going to pick up right now 3. So 12. Now the next one has to be the next smallest connected. What do we have to consider? Right now 12 has been picked up already. However, we have 18, 24, and 16, and 28, of course. Right. Now obviously the smallest in this bunch is going to be 16, so we're going to have here 2. And this is going to be 16. Now, since this one has been picked up, I'll just eliminate it. And right now, let's actually look what is the next smallest. So we have 28, 14, 18, 24, and the next smallest is going to be is definitely the 14 bit. So here is going to be 14. Okay, and right now I've fulfilled the minimum spanning tree. I've got all the vertices, right? So all the vertices are there. And let's count the edges. 1, 2, 3, 4, 5, 6. So 6 minus 7, so 7 minus 1, right? 7 number of edges of a minimum spanning tree equal to the number of vertices minus 1, right? So we have 6 edges and we have 7 vertices. We completed it. We got actually the minimum spanning tree, right? So what is the cost? The cost of this guy is going to equal to, so 10 plus 25 plus 22 plus 12 plus 16 plus 14, which is going to be 99. Okay. And this is prim. This is it. Now, it is important to understand that, and I'm going to write it even in yellow, because it's also important to mention it here. So in prims, a graph has to be a graph has to be connected. Okay, so if I actually give you a graph that looks like this, so 1, 2, 3, then we have here 4, 5, 6, 7. So we have islands in this graph, right? This is one single graph. However, they just simply happen to be disconnected. So you have islands here. Now, a prim, there is no solution for this in prims. There is no solution for MST in prims. Why? Because if you try actually to dig at this, again, MST is an optimization problem, is a greedy method. You need to get the minimum spanning tree. Now the problem is if you have costs, for example, let's say you are actually like saying all the time, give me the next connected. You're gonna say, okay. So this is going to be, for example, the less connected, and this is it. Right now, we're trying to give me the next least connected edge. You will actually stop because these edges are not actually connected anymore, right? These vertices are not connected as well. So right now, you will not have a minimum spanning tree. Just prims will just fail. So this is just what a prims is all about. Now let's talk about Kruskal's. Kruskal's is similar to prim. And let me actually grab this. And I'll try to erase these guys as much as I can here, here. And maybe, well, let me zoom in. Oops. Okay, let me just connect these guys, or there we go. So I'll zoom back and a little bit back. All right, now let me, I will copy this. We'll use the same graph. So can I copy? I think I did this once. There we go. Copy. And paste. There we go. So assuming that you have a graph like this, and you would like to find the minimum spanning to use in Kruskal's. So using Kruskal's, the first step will be get edge with the minimum cost, the same as prim as a start with, oh man, hang on. Of minimum cost. So, and this is the and this is like the first step. And I'll write the second step immediately here. Second step, get the next edge or the next minimum or smallest cost edge, not necessarily oh, how do you even spell that? I forgot. Not necessarily. Oh, okay, I'm gonna actually like rewrite this a little bit differently because I honestly cannot remember. Not necessarily. So get the next minimum. Well, you know what? I'm gonna find it out. There we go. So not necessarily connected. There we go. So not necessarily connected. Make sure that you don't form loops, because again, this is a tree and a tree doesn't have loops in it. So by definition, you should avoid them. So right now, we will actually solve it. So for this solution, we're going to have, so 1 and 6. So this is the edge with cost 10. Now the question will be here is, what is the next smallest? So the next smallest in this whole set is 12. So you're going to have here 3, 4. So this is 12. Now you're going to actually try to find the next smallest, which is going to be, well, actually, is it the smallest? Yes, it is, isn't it? So 10, 14, 16, 18, 12. Yep, this is the next smallest. So the next smallest is going to be 2 and 7. So 2 and 7, right? So this is the next smallest. Now the next smallest is going to be what? 16. So you add it here. So this is, what was this one? 14, I guess. Yeah, this one's 14. Now, here is the interesting part. If you say that the next smallest is going to be 18, you will actually form a loop, which you can't. So this part is forbidden. So you cannot actually pick that one up, right? So you're going to say, aha, okay, give me the next smallest. And the next smallest for you will be 5, right? 4 and 5. Now, the next smallest, which is this, is going to actually form you another loop, which you are not allowed to do, right? So the next smallest will be this, which is going to be 25, right? Now, this is actually giving you the exact same result in this case. So here, MST, the cost, is going to equal to 99, okay? Now, if you have noticed here, we picked up always the next one, but we have this overhead check of do we have a loop or not, right? That's the first thing. The second thing, which is important, is that both spanning tree, or sorry, both, let me write it here a little bit back. So both minimum, let me write it in a shorthand then. Both minimum spanning tree algorithms give all, not always, not give, always should give the same cost. And you know why? Because this is a greedy method and it is a minimization problem. So you have to find the most optimal solution. And there's only one optimal solution for a given problem. So both MST and PRIMS should actually provide you identical solutions. You might get a different tree. It could happen that you get a different tree, but you cannot have a different cost. If you have different costs, that means something is wrong with your algorithm. Okay? So it might happen. So let me actually write this down. It might happen to get different trees. But you will always get identical cost. So this is very important thing to mention here. Okay, so let me write this down here as well. So this and this don't pick don't pick up these. You will form a loop. There we go. So this is just a note here for you guys. Okay. Now, cross calls can actually work on this connected graph because if you have noticed, I'm actually getting not the next connected, but just the next edge. However, you will not get if you have something like this. So if you have something like this, and you have something like this, you will not get one spanning tree. You will get actually two of them, right? So you're gonna get this one, for example, and this one, and maybe you will get this one, and this one, for instance, right? So, however, you cannot get a minimum spanning tree because you got right now two of them. So, cruise calls can run on this connected graph. However, you will get 2 MSTs. So you'll get 2 of them. Okay, so that's the important bit. Do you guys have any questions regarding minimum spanning trees? Is it all clear for you? Peeps, are you still alive?
It's clear. It's clear. Everything's
Uh-huh.
clear.
Okay. Okay. All right. So, let's move ahead with Dijkstra then. Okay. So Dijkstra is a greedy algorithm for finding the shortest path from one node to all other nodes in the graph. Okay. And it is fairly easy to work with. Just it needs a little bit of clarification here. Now, let me actually write it down. So it's called Dijkstra, not Dijkstra, just to be clear here. This is how his name is pronounced. So Dijkstra algorithm. So Dijkstra algorithm is what we usually call is a single source shortest path algorithm, SSSP. And literally people writing it, like if you look on the internet and you find like single source shortest path, people will just write it SSSP. Okay. Algorithm. So, whoa. Oh man. What the heck? SSSP algorithm. Okay. Meaning you have to find the shortest path from a starting vertex to all other vertices in a given graph. Okay. Now, since we are trying to find the shortest path, this is actually an optimization problem. Okay. Minimization problem, meaning that the algorithm which we are trying to use here is actually a greedy algorithm. Okay. Now, Dijkstra can work with a directed and undirected graph, so it can work with directed and undirected graphs. Okay. So it can work with directed and undirected graphs. Now let me give you an actual example so we can build up from there. So we're gonna make something really simple, small, and then we just simply like get a little bit more complicated example. So for example, we can say that one, so if you have, for example, if you have a graph that looks like this, 1, 2, and 3, okay? And then this is the cost 3 of this part, and this cost is 5. Now, this is what we call a distance. So the distance from 1 to 2 is 3, or the weight from 1 to 2 is 3. We usually call it the distance. In Dijkstra's like algorithm, we look at it like distance, okay? Now, assuming we are starting from 1. Assuming we're starting from vertex 1. We pick up the shortest path from vertex 1, right? So the only thing which is connected to 1 is 2. So practically speaking, we say, aha, okay, so what is the cost of 2? The cost of 2 is actually 3. So I'm going to write this down in a different color here. So this is 3. Now, 1 is not connected to number 3 directly. And because there's no direct connection, this will be put into infinity, okay? Or the largest integer you have on your machine. Or your machine can support, right? The largest integer your machine can support. And this just because you cannot reach to 3 directly. You just can reach it only through 2. You don't have a direct connection. Now, since we have actually 2 here, once we have reached 2, right now we see what else is connected. And we need to choose the one with the minimal cost, right? And the one with the minimal cost is like the only thing which is connected happens to be 3. Now, what you look at is say, aha, okay, so how can we update the cost of 3? So the cost of 3 is going to be, the cost of this guy is going to be 3 plus 5 is going to equal to 8. So 8 is less than infinity. So we're going to update that. So we're going to erase this and we're going to put here 8, right? So this, we just simply do update the actual weight. This update, which we have done, is called relaxation. Okay, this is what we call the vertex relaxation. So let me write this down here. So the vertex cost update is called relaxation. Okay. So what is exactly like how do you write this in an if statement, or how would you algorithmically describe it? So what we say is if the distance of u, assuming that this guy is u and this guy is v, okay? In this case, so this is u and this is v. So the distance of u plus the cost of u to v is less than the distance to v, right? So for example, we said that 3 plus 5, so the cost of u, so the distance of u, so this was actually 3. And the cost of from going to u to v, so if you add these together, so 3 plus 5 is equal to 8. If it is less than the distance to v, which was infinity, then we actually update it, right? So we update this d of v equals to d of v plus c of u and v, right? You update that. Otherwise, you don't, right? So this is basically the algorithm for it. Now that we have an understanding of how to do relaxation or how to work with this thing, let us actually get an example that is actually quite famous in the books. So if you look at the books which I've given you, was the introduction to algorithms and data structures and the data structures and algorithm analysis in C, those the green and the white books, from the one from MIT Press and the other one I forgot. I think it was Addison Weasley's print. They actually, both of them, they describe, I think, I cannot remember exactly for the Addison Weasley's one. I know for the green book from MIT Press is the one that has the exact same diagram. So, and even our professors, they showed us the same diagram. So for the sake of holding the tradition, I'm going to give you the similar example. So 1, 2, and I'm going to make it directed 2, 3. And this is going to be here. I'm going to write the weights later. 5, 4, and this is going to be 6, and this, and this, and this, and this. Let me get this actually a little bit nice. There we go. Okay, now let's give some weights here. So 7, this is 2, this is 1, this is 4, this is 3, this is 2, this is 5, this is 1. Okay, assuming that we are starting from 1. So I'm going to write here, assume starting point or starting vertex rather is 1. Okay, so this is your S. This is your start. Okay, now let's actually calculate the cost. So by default, the node or the vertex which you are standing on has a cost of 0 because you are here already. Okay, so we usually don't care about it that much. However, we care about the one which is directly connected. So the one directly connected is from 1 to 2 is actually a cost of 2 because you go here to there is 2. The one from 1 to 3 it has the cost of 4, right? Now the question here is, can you reach from 1 to 4? You can't. So this is infinity. You cannot reach from 1 to 5. This is infinity. You cannot reach from 1 to 6. This is infinity. Because you cannot reach directly. There's no direct connection whatsoever. If there was a direct connection, you update, right? You put the calculations. Is there anything else we can do? No, we don't. Now, what you're going to actually do is pick up the vertex with the smallest cost. This is coming up next. So the second step, pick up the vertex with the smallest cost. Now the vertex with the smallest cost is actually 2. Okay. Now I'll actually pick up another color here, so I can actually like show you like how the iterations of steps is actually evolving, and I will pick up another color for every iteration or every relaxation. And right now we see, okay, so from 2, what is connected? We cannot actually go to 1 because 1, we have been there. This is for one thing. The second thing is there's no direction to it, right? You cannot reach from 2 to 1, actually, because of the direction of the vector or the graph. So the only 2 vertices which you can reach to is 3 and 4, right? From 2. So 2 plus 7 is 9, which is less than infinity. So we do the relaxation here and we actually update this and we say, let me undo this and make this a little bit. Yeah. So this becomes 9. 2 plus 1 is 3, which is less than 4. So we actually cross that out or update that to 3. and we did our relaxation. Now, we pick up the next smallest cost. We have right now 9, 3, and 2 infinities, right? Infinity here and infinity there. So what we do is we pick up the, since we say we need to pick up the next, we pick up the next smallest. So the next smallest is actually 3. So from 3, where can we connect? From 3, you cannot connect to anywhere other than 5, practically speaking. So 3 plus 3 is actually 6. So let me actually update this right now. So I'm going to use this color, and I'm going to write here 6. Okay. Now we pick up the next smallest vertex with the least, with the smallest cost. So what is actually the vertex with the smallest cost? So let's see, we have 9 and 5. So sorry, 9, which is 4 and 5, which is having 9 and 6. So we pick up 6. So 5 can be reached, can actually, sorry, can reach to 4 and can reach to 6. So we do actual relaxation for both of them. So let's give this one a try. So 6 plus 2 is going to equal to 8, which is less than 9. So we update that. So we do a relaxation. And let me pick up red. So this is going to be out. And here we're going to have 8. Now, 6 plus 5 is 11. 11 is definitely less than infinity. So we cross that out and we put 11 in. Now, we pick up the next smallest one. Now the next smallest one is either 8 or 11. So we pick up 8. Now 8, now the vertex 4 with a cost of 8. If we look at what is exactly connected directly to it, we can see it only connects to 6. So if it actually connects to 6, let me pick up a different color. Now this is going to be a little bit interesting. So modify tool. Yeah, let it be something like what? Green, maybe? Darker green, fine by me. So 8 plus 1 is 9. 9 is less than 11, so we update that. So we have 9. Okay? So right now, by this, we are done with Dijkstra. We have found the shortest path with the minimal cost from a starting vertex to every other vertex. So if you would like to reach from 1 till 4, the actual cost of it will be 8. If you would like to reach from 1 to till 5, the actual cost will be, for example, I don't know, 6, for example, right? So this, basically speaking, it's a single source, shortest path to all other vertices in the graph. Okay. Uh, do you guys have any questions regarding this? Couple of things here until you ask the questions. If there are no incoming edges to a vertex, it is considered to be unreachable. Okay, this is super important. Because, for example, if I tell you that the starting point, let's say, is 4, right? You can reach from 4 till 6, but you cannot actually reach 1 because one, you cannot, there are no arrows incoming to one. So for you, one will be unreachable, will be always infinity. Okay. So this is very important point to mention here. Let's say because Dijkstra works with undirected graphs as well, some people might get confused by it. And if you get confused by it for any reason, so for example, if I give you a graph that yeah, it doesn't matter the number of vertices, to be honest. So let's say I'm giving you a graph that looks like this, and I'm telling you find me the Dijkstra for it. And it's undirected. You can convert any undirected graph to a directed graph, because this edge, for example, it means that you can actually go this way or go this way. With these edges, you can go this way or you can go that way. And with this edge, you can go this way and go that way. So this is equivalent to this. Okay? So you can actually convert a directed graph to an undirected graph. Sorry. What did I say? Okay, you can convert undirected graph to a directed graph, just to be clear here. In case you got confused, or in case you got an exam, for example, undirected graph, and then you have to, and you got used to the directed graphs, for instance. I think this is it. When it comes to Dijkstra, I will stop recording.